Okay, so so I'm so so this is really a clarification regarding definitions, and we will use a cancellation lemma in a way that I'm just expanding on what I said in the last class and what I said in the notes. Okay, so supposing I want to define a vector space. Okay, I'll give you 3 sets of definitions. Okay, and then they are actually equivalent because, and to go from one to the other, in one direction it will be obvious, and in the other direction you will need to work a little, and in particular it will involve the cancellation lemma. Okay, and then I will advise you to remember a version of the definition which is which has the full thing, including, so there is a minimal set of axioms that you need to define a vector space, and then there will be a few other properties that follow from the axioms, which I can, without contradiction, put in with the axioms. Okay, and then my recommendation is that you remember the definition with these added things, because that is a whole package that you have to remember and keep using when you think of vector spaces. Okay, there is no virtue in just remembering the minimal definition. You don't get any punya by saying, okay, this is the definition and this follows, because when you are working with the definition, you want to be able to do it very quickly and without thought. Yeah, you need. Okay, so let's do this. So there is the definition. Let me call this definition 1. Well, I shouldn't repeat everything. So a vector space is a set V together with maps, and sometimes they're called maps rules. Rule is an informal way of talking about a map. Rule is a prescription. Rule is a way. Okay, there are 2 maps, V cross V to V. This map is called vector addition, and R cross V to V. This is called scalar multiplication. Okay, so that reminds me that I am going to only talk about real vector spaces till further notice. Okay, and the elements of the set will be called vectors. So, and this rule will be denoted like this, given, let me stick to my earlier notation. V plus W, and lambda V maps to lambda dot V. By the way, this symbol is pronounced maps to. Such that, and now I will give us several definitions, 3 sets of definitions. 1, V plus W equal to W plus V for every V W. 2, V plus W U plus V plus W is V plus W. There exists a vector 0V such that V plus 0V equal to V for every V. So this is 3. For every V, there exists a vector minus V such that V plus minus V equal to 0 V. Then lambda dot V plus W is lambda dot V plus lambda dot W, and 6 lambda dot mu dot V is lambda mu dot V. Okay, I hope I have not forgotten any important thing. Let me quickly, let me check. Just give me a second.
Sir, the existence of a one, I mean, 1 dot V equal to V.
No. We will come to that. We will come to that. If you look at my, yeah. Thank you. Thank you. And 7, 1 dot V equal to V. Yeah, thank you. So, right. So this is definition. So let me call this set the red set, the red definition. Okay. Now let me put up another definition, which I will call blue.
Sir, this.
So somebody, tell me.
Sir, this 1 dot V equal to V, that condition actually says that there should exist such a one in the field, right? Such that for all.
Well, what is the field? What did I start?
Yes, sir. It's a real number. Oh, yes, sir.
Real number. Yeah. Okay.
Sir, even if the field is real numbers, won't the one in the field depend on how the dot operator is defined?
But that is how you start with. Now you are given the dot operation to start with. You are given 2 rules, and then you are imposing conditions that the rules have to satisfy.
Yeah. I understand that. So if the dot operator, if it is not multiplication, if it is something else.
What do you mean if it's not multiplication? What is multiplication?
Like here, the dot operator, I mean the lambda comma V rule, instead of, for example, it being lambda dot V, if it is something else, won't the one change?
I think, look, before you are, look, your question doesn't make any sense. You are
no. Yeah.
Wait. Before you talk, just listen to me. You are given a set.
Okay.
V. You know what the set of real numbers is.
Yeah.
Okay. You have to give, first of all, 2 rules. You have to give a map from the Cartesian product of V cross V to V. That's called addition. And you have to give another rule, which will be a scalar, some rule. It is some map.
Yeah. Yes, sir. I understand.
It is given to you.
Yeah.
But now, if you just give some arbitrary rules, it will not make your set a vector space. For these rules to make your vector space, these rules have to satisfy certain conditions. One of them is that when you take in the Cartesian product of R and V, when you take the pair 1V, where 1 is the real number 1.
Oh.
That should go to V.
Oh, okay. I what I thought was
no, it's okay. If you understand, that's fine. What we thought is okay. Okay, so let's call this the blue rule. Blue definition.
Sir, isn't the another property that lambda plus mu into v equal to lambda v plus mu v?
Just one second. Let me finish this. Yeah. So I'm going to call this the blue definition, and on the left you have the red definition. Now, what was the question?
Isn't there another property that lambda plus mu into v equal to lambda v plus mu v? Lambda mu scalars.
And you mean distributivity in the first one?
Yeah.
One variable. Let me see if it is there in the definition. Yeah. Thank you. Thanks a lot. Yeah. Yeah. So. Okay, so you have the red definition and you have the blue definition. Okay, so there are two possible sets of definitions for vector space, and a priori these will define different sets of different kinds of objects. And what is the difference between the two definitions? What is the difference between the red and the blue definition?
The uniqueness.
Exactly.
The uniqueness.
Okay. So the difference is that on the right I have unique, and here I have unique. Okay, is everybody with me so far? Yeah.
Yes, sir.
Yes, sir.
Yeah. So
Yes, sir.
now clearly, if I have, so let me call the blue guy the blue vector space, and let me call the red guy a red vector space. Okay. Now clearly, if I have a blue vector space, it's a red vector space, because a red vector space, I don't care if the zero vector is unique. I don't care if the minus v is unique. So if I have one zero vector, I'm happy, and and if I have for every vector I have one minus v, I'm happy. So I will. So every blue vector space is a red vector space. So there are a priori two different kinds of mathematical objects. One class of objects is something called a blue vector space, and some class of objects is a red vector space. The Democrats and the Republicans. Okay, and a priori these guys hate each other and have nothing to do with each other. Okay, and but when I go around, I will find that whenever I find a red vector space, in fact, it's actually whenever I find an example of a red vector space, it is in fact a blue vector space. In other words, whenever I find a vector space where a set where all the axioms are satisfied, I can never find an example where there are two distinct vectors which play the role of the zero vector, and I can never find an example where for every vector there are two negatives of that vector. Then I begin to suspect, maybe there is something that guarantees that in fact every red vector space is actually a blue vector space. And so I prove a little lemma, which is the cancellation lemma, which I can use to prove exactly this fact. And then I find, very good. So why do we even need the first definition? You mean the red definition? Shakti Chauhan. Yeah, right. So that's a good question. Why do we even need the first definition? Okay. Now let me go ahead. Okay. So let me give you further definitions. So you are saying if once I have the cancellation lemma, I can even take the second blue definition and use it. right? But in fact, let me now give a green definition where everything is true, as in the blue case. But in fact, I will say for 2, I will say there exists unique 0v such that v plus 0v equal to 0v plus v equal to v. Then I'll somehow so this is 3. 4, for every v there exists minus v such that v plus minus v equal to minus v plus v equal to 0v. Okay, so this is a green definition, and then the others are the same. Okay, now so now a priori, now this is even there is a new class of vector spaces where this is true. So because there is a difference between the blue definition and the green definition, but actually, if I have the blue definition, the green definition follows because of the condition 1, addition is commutative. So if I know that v plus 0v is equal to v, 0v plus v is also equal to v. So there is even a stronger definition I can put, which Sadhu Khan, you have a question.
Yes, sir. I wanted to ask that while doing sums, do we?
No, wait. So let me complete this train of thought, if you don't mind. Okay. Then you can come back to this. Please please stop me and ask me after I finish the thing. So there are a few other. So I can strengthen the definition in ways that actually follow from the most compact definition. And this is what I mean by remembering the whole package. Okay. For example, I can add from all these things, it follows that if I take the 0 real number and multiply any vector by v, I get the 0 vector. It also follows that if I take the number -1 and multiply any vector by v, I get minus v. It follows. Okay. So I can do two things. I can put this in the definition and say that this definition is equivalent to the sort of the red definition, or I can go with what you suggested and just keep the strongest definition. And my advice is, remember, put all these properties into a package. Remember that some parts of the definition follow from a smaller set of axioms for a vector space. And you should know how to prove it. If somebody challenges you, how do you prove that the strongest definition follows from the weakest definition? Then you will say, there is the cancellation lemma, or because of commutativity of addition, I can do this. But when you remember the definition, just remember the whole package, because the whole package is what you work with instinctively. When you are doing a computation, you should be able to replace -1 times by v by minus v without thinking. Okay. So this holds, in many contexts, that sometimes you have a definition in which some parts of the definition follow from the others, and it's more efficient to just remember the whole definition. Unless in some cases, you have to make a big leap to go from the smaller definition to the big definition, involving many theorems and a lot of hard work, in which that's a theorem. If it's a small leap, just put it into the package. Is this clear? So people who are confused about the cancellation lemma and the definitions, I hope this helped. Now, I think Sadhu Khan was Saptashi. You asked something about problems. Yeah. So
Yes,
now I will answer that question and move on to something else. Go ahead. What is your question?
So you said that it's best to remember this as a whole package, but
Yeah.
while solving problems, which one is the standard to assume? Like if we assume
No,
one,
no. See, this is your judgment. I say, don't worry about problems and what we will see. It never happens, at least in my exams, that I am not like a lawyer. Okay, I try to see. You have to use your judgment. What is it that the examiner expects you to understand and use? This is not really unless if it is, if I wanted you to use a cancellation lemma, I will just tell you, prove the cancellation lemma from the minimal definition. I will ask you outright. Okay, it will not happen that I kind of expect you to remember this is not a court of law. We are interested in getting at more interesting aspects of mathematics.
okay, sir.
Yeah, you understand. So don't worry. You will know, at least if you get, your TAs might penalize you. You can come to me. I will rectify it. But it rarely happens that you get, you lose marks because of such legal issues.
So
Yeah.
So since you mentioned TAs, I would just like to ask who are RDs for algebra?
No, I have. Okay, I will tell you. I'll tell you. I was going to send a mail with actually contact details and everything. I will do that. Why don't I do that? I will do that quite soon.
Okay. Yes, sir.
You have, I think, about 6. So you have a fairly strong team. So yeah. Very good. So.
Sir, just 1 second. Could you repeat where exactly we use the cancellation lemma in the second definition?
Okay, because I didn't do that today, so it's not a matter. I did that in the last lecture, I think. It's there in the notes. Okay, so I want to show that every red vector space is a blue vector space. In other words, there are 2 things. If there is 1 0 vector, that is unique. If there are 2 0 vectors, they are in fact the same. Okay, that is okay. And the other thing is, if a vector has two additive inverses, if there is a minus v1, there is a minus v, and there is a okay. So the basic thing is, how do you put this uniqueness at 2 places? Okay, so let us prove one of them. So okay, this is good. How is uniqueness lemma, cancellation lemma used?
So we just assume 2 different things and show them to be same, right?
Exactly. So I will not appeal to the cancellation lemma. Let's just do it. I mean, the cancellation lemma is we will just derive it as we go along. Okay, it will be part of the proof. Okay, so want to show, yes, Srimati Shrikant to everyone asks, I don't understand the definition between the blue and green definition. Shrikant, can I call you Shrikant? Yeah. So look at can you see what's on the screen? And if you can, it's somewhat easier if you can speak. Can you speak? Or do you have a problem with your mic? Mic isn't working. Very good. So then I'll keep the chat open. So can you see you see the two definitions on the screen? What is the difference between the two definitions? As was pointed out, on one side you have unique, on the other 2 occurrences of the word unique, and on the other side unique, the word unique doesn't appear. Do you agree? Okay, so that's the difference.
Sir, she is asking about the difference between the blue and the green one, not the red and the blue.
Okay. Yes. I am so sorry. Between blue and green, well,
you haven't assumed uniqueness of inverse.
No. So between, this should be unique. Yeah. So the difference is that in the blue definition, I don't have this part. I don't have this part, and I don't have this part. Srimati, are you? Do you see that? Yes, yes, yes. So in the definition, it's not there, but it follows from the commutativity. That is that. That is the point. So I might as well, yeah. And it's even from the point of view of aesthetics, it seems silly in the definition to single out one way of adding when the other way of adding is also equally important. And in fact, both are, you might as well put it there. Okay? But people who have very legal minds will take a minimal set of axioms that defines an object, and then they will say many other properties follow from that. And then the minimal set of axioms will be called the definition, and so on. So there are two things wrong with this. First, often this minimal set of axioms is not unique. There could be a slightly different choice of the minimal set, which will also give exactly the same object. And more important, in practical life, you never think of the object in terms of the minimal definition. You think of the object as a package. Okay. Very good. So how is the cancellation lemma used? So want to prove if there exists 0v and 0v prime such that v plus 0v equal to v and v plus 0v prime equal to v for every v, then v 0v equal to 0v prime. So in other words, if there are two zero vectors, they are the same. Okay, so let us do that. V plus 0v equal to v, which is v plus 0v prime. So in fact, you don't even need for every v. So if this is true for every v, it's true for some v. So I can take one v for which this is true. Now you take minus v, because minus v exists. And by the way, I don't need to assume that minus v is unique. There exists one minus v. Then add minus v to both sides. Add minus v to both sides. Then minus v plus v plus 0v equal to, I got this wrong.
Can't we just do it without the existence of minus v? Just 0v plus 0v dash is 0v, and it's also 0v dash. So 0v equals 0v dash.
Yeah, thank you. Yeah. So, thank you. Very good. Yeah, look at 0v plus 0v prime. On the one hand, so 0v plus 0v prime is 0v, because thinking of this, so here let 0v prime play the role of the zero vector. So then you get this. Now on the other hand, 0v can play the role of the zero vector. This is equal to 0v prime. So you have this. Thanks a lot. So you understand. So this is a small step, and so all these such arguments are what the cancellation lemma says. So what is the cancellation lemma? Cancellation lemma, given u v w such that u plus v equal to u plus w, v equal to w. If I have three vectors such that this is true, then v is equal to w. Rohan, did you want to ask something?
No, sir.
Okay. So very good. So that was cancellation lemma. Now let me see what is the next thing on the Ripunjay, you have a question. Yeah.
Yes, sir. So basically, what we basically finally arrived at is.
I have one request to everyone. Please don't say basically. I am somewhat allergic to the word.
Okay, sir.
It is not a.
Okay, sorry, sir.
It is not helpful in English to say that. Really, no.
Sorry, sir.
No, don't say sorry. Just examine your conversation and see if in mathematics in fact in life it helps to say basically, because very rarely when somebody says basically are they saying anything that's simpler, or often it doesn't even mean the same thing. So just yeah. Go ahead. So what do you want to say?
So I wanted to ask that if we assume that there is a unique zero vector, then that implies that we have a unique inverse. And if we assume
No. I don't want to now begin to get into no. There's a difference between the red definition and the white and the blue definition on the surface, and in fact there is none. I don't want to now further slice and dices and say, okay, you can assume uniqueness in one, but not in the other. No, let's not spend time on that.
Okay, sir.
Yeah.
So, yeah. Okay.
Shakti, you want to ask something? Your hand is up.
Sir, in the previous proof, did we just use the converse of the exam, like v plus 0v is equal to v?
No. See, forget about. So in fact, the proof was simplified. I began. So this is, first of all, do you agree that this is what we want to prove?
Yeah.
Sorry, we want to prove this.
Yeah.
Right. So now the suggestion was you just look at this expression, you take your two zero vectors and you add them up.
Yes.
Now, because 0v prime is a zero vector, this sum is equal to 0v. Right? That is because of this condition. Using this, you see this equality.
Yeah.
Now, using this, you see this equality.
Yeah.
Okay, so this guy in the middle is equal to both 0v prime and is equal to 0v. Therefore, 0v prime is equal to 0v. That's all.
Yeah.
Okay.
Got it.
Yeah.
Got it.
That's a yeah. So.
So I had a small nitpick. So when you're when we're proving this, for example, suppose in a quiz or something, like do you have to show commutative separately? Because
no, I don't want to deal with the nitpick. Commutative is assumed right at the beginning. Just go back. In all my definitions, commutative is assumed.
Yes, so will we have tried 0v plus 0v dash is equal to 0v dash plus 0v?
No, that is my statement. That in fact, oh, you mean here?
Yes, so when we're showing that the left hand is equal to the right side.
No, you use commutativity if you wish.
Yes.
Yeah. Okay. You okay. Okay. You use commutativity. Okay. Commutativity is used. Okay. Yeah. I agree. That was a genuine nitpick, and it was a nitpick. Yeah. Very good. So now maybe this is a good time to take a break and come back after say 5 minutes. Can I do that? Yeah. Okay.
Yes, sir.
Bye. We resume. Very good. So yeah.
Sir, can you just tell me once again that why do we need all the three definitions separate?
Sorry, I don't know why. Yeah. So what was the question again? Sorry.
So can you tell me once again that why do we require all the three definitions separately? And why not a single one will work?
No. well, the third definition was somewhat, it was a notional thing. I just wanted to highlight so there is a set of axioms. So look, just concentrate on the two possible definitions that I gave you. Okay, and so clearly the red definition is in some sense more logically more satisfying one, because as far as we know, none of the 8 things can be dropped without changing the meaning of the definition, because none of the 8 follows from the others. Okay, but if you look at the blue set, that whether I have a unique, the two occurrences of unique or not in the definition seems irrelevant, because even if the word unique was not there, in fact, that would be true for any vector. As I kept saying, any red vector space is a blue vector space. Okay, so from the logical point of view, you should take the red definition as the definition of a vector space, derive by relatively trivial steps a few additional properties, and say, okay, a vector space in fact satisfies these additional properties. If there is a 0 vector, in fact, it's unique. If the vector has a negative inverse, additive inverse, it's unique. Then -1 times the vector is minus the vector, etc., etc. So these will all be lemmas or propositions, or if you're feeling grand, theorems. Okay. And so I could have developed the whole course like that. But I'm saying that that is not efficient from the point of view of your working. You should, when you encounter an object called a vector space, you should remember the whole package, and just for heaven's sake, just think of that as a definition. But be aware that that is not the minimal set of axioms to define a vector space. That is all. Ishan, is that okay?
Yes. Thank you, sir.
And there were some questions in chat. Shakti Chauhan asked, on 20th we were 77 people today. Today it's 71. Why? I have no idea. So that is yeah. Very good. So now can I resume the let us now. So again, I realized that I should have possibly spent more time with definitions before I proceeded with more abstractions. But nonetheless, I think it's good to define the notion of a linear map. And I hope, which I did in the last lecture, it is there in the notes, and I hope you have understood what a linear map is. And what is an isomorphism? And then there is an exercise that asks you to do. And then I think I defined the notion of a subspace. Now, there were questions about the definition. People wrote to me saying that, essentially saying they don't understand the notion of a subspace. So let me first ask you, linear map T V to V tilde isomorphism. Can I take it that you understand this and you understand this? Because now the next topic I want to talk about is subspace. So before I go to the subspace, I want to, and then once we deal with subspaces, I will go to examples. And the rest of the class will deal with examples. In which context we will talk again about linear maps and subspaces. But before I begin, can I take it that you understand what a linear map is and what an isomorphism between vector spaces is? Okay.
Yes.
Yeah.
Yes, sir.
Yeah.
Yes, sir.
Very good. So now what is a subspace? So a subspace is, to talk about a Shakti Chauhan, you have a question. Yeah, tell me.
Sir, if T is a linear map and it is bijective, then its inverse will be always be linear. So it is isomorphic.
Exactly.
So
That is
is it true for every vector space, or is it just true for real vector space?
Actually, this is true for every vector space. Yeah, this is the field is irrelevant here. Yeah. By the way, there was a question that was that somebody sent to me. Which essentially asked if I could talk about linear maps between vector spaces over two different fields. First of all, so let's not open that can of worms now. Let us just say we are only dealing with real vector spaces now. So all vector spaces that we encounter will be real. And even in the future, in general, when you say linear maps, it's understood that you're dealing with vector spaces. The underlying field is fixed. Okay, so this is the answer to somebody who asked a question to me by mail. Now, subspace. Very good. So to talk about a subset, you need a set, right? So when you say something subspace, clearly a subspace makes sense only in the context when you already have a vector space given. Okay, so a subspace is not an object in itself. It is a sub-object of a bigger object. So the bigger object has to be first given. So a subspace always means that you are given one vector space and something else. Okay, so you are given a vector space V, and then we can talk about subspaces. Okay. So now, what is a subspace? First of all, it's a subset. So this is a vector space. But not every subset of a vector space is a subspace. Okay. So what is it that makes a subset of a vector space a subspace? So there are two conditions. One, W is closed under addition. So what does that mean? I will say closed under addition. And two, W is closed under scalar multiplication. So what does the first condition mean? That means that if I take two vectors in V which belong to W, then their sum also belongs to W. The second condition means that if you take a vector in W and multiply it by a scalar, the result also belongs to W. And so now there was one crucial word. It is again only if you are a lawyer, but in this case, it's important that you be a lawyer, is that there is one word that was missing, namely that you should demand that a subspace is non-empty. So it's a non-empty subset. So in the first version of the notes, and possibly in the last lecture, I forgot this important qualifier that for a subset to be a vector space, the first condition is that it should be a non-empty subset. And then you can demand that it's closed under addition and under scalar multiplication. And then it becomes what we call a subspace. Okay, now, why is this a good definition for vector space? It is a fact, and it's quite easy to see. Fact. So I can be formal and call this a theorem or a lemma. If W is a subspace, then it is naturally, I will say something that's not quite mathematical. It is not, it makes sense in English, but to make it mathematics, I need to be precise. Then it inherits structure of a vector space from V such that the inclusion map W to V, which I call I, is the linear map. So this is not a mathematical statement because inherits has no meaning. So let's make it mathematical. So I call this fact prime. If W is a subspace, there is a unique structure of a vector space on W such that the inclusion map W to V, which I call I, is a linear map. So so I'm not proved fact prime. Fact prime is what you have to prove, and then once you prove fact prime, then it makes sense to call such a subspace a subspace, because when you hear subspace, you're supposed to think sub vector space. A subspace is just a compact way of saying subspace is just a compact way of saying sub vector space. This word is never used, by the way. I just invented it. You always say subspace. So this is not difficult at all. So see, supposing I'm given W. So how would you define minus W, for example? So what is, for example, what is 0 W? Clearly, it has to be 0 times any vector in W. Okay, W is times any vector in W. So I'm not giving the proof of fact prime. I'm leaving that as an exercise.
So any vector in W is also a vector in V.
Exactly.
So yeah, that will make it 0 V.
Yes, but W. So W is a subset of V. Okay. So any vector that you get in W will be a vector in V. So,
yes, sir. So the zeros are the same precisely.
Zeros are the same, exactly. Yeah, yeah. So, but you have to show that 0 V is contained in W. Okay, that is another way of giving this argument. So, okay, let me just say that. Thank you.
Sir, since W is also a vector space in itself, and we know that every element.
Wait, Shakti, wait. That is what I'm trying to prove. I'm trying to prove that a subset which is closed under addition, a non-empty subset which is closed under addition and scalar multiplication, has a structure of a vector space. That is what I'm trying to prove. That is what fact prime is. Satya, yeah, Satya, you have a question.
Yes, sir. Can you please explain what an inclusion map is?
Inclusion is when I have a subset of a bigger set. So that is included. So when I have a subset of a bigger set, then there is a map from the subset to the bigger set, namely take an element of the subset, think of it as an element of the bigger set. Okay, so it is more a psychological thing than anything. So you have the set, and I have a subset, which is this thing. But then I want to think of that subset as a separate set. Because that subset, the moment I begin to refer to the subset, it has its own existence. Right now, if I take an element of the subset, that element has two roles: first as an element of the smaller set, and then as an element of the bigger set. So there is a map from the subset to the bigger set, map of sets. So it's useful to actually think of this map, give it a name, And usually, this map is usually called an inclusion because it's very suggestive. The word inclusion is very suggestive, and you give it a name. I is a no-brainer, so you call it I for inclusion. And this is not just a fuss. It's a very useful thing to do. You will find as you go along that it's very useful to when you are given sub-objects of mathematics of bigger objects. Is usually it's a subset. Objects are sets with structures. Then it's really useful to take the subset, sort of remove it a little bit, and then sort of consider the map. If you have, for example, if I take the closed interval 0, 1 in R, then every real number between 0 and 1 has two roles. First as an element of the closed interval, and then as an element of R. And then the map which takes that point in the closed interval to the point in R gives you an inclusion of the closed interval to R. It's really a useful thing to do. Okay, and so so now you understand. So you see, I think my informal way of talking is might confuse. So let me just call this lemma. Okay, I will call the first thing fact because the first thing is not mathematically formulated. So it's permitted to call it fact. Let me call this proposition, if you don't mind, because it's important. It's easy, but it's important. Proposition. So proposition is a result. I have to prove it, but it is a mathematically precise statement that you should understand. There are two raised hands. Let me see. Yes, let me repeat. Shakti, you are continuously worried by scalar. Yes, by scalar, I mean, about which field you're talking about. It's a legitimate question. Always are. So when I say scalar, I mean a real number. What is a fact prime structure? Did I say fact prime structure? Did I say something like that? Rajagopalan?
I heard it wrong.
No, I didn't say. Gosh, just shows that I. Okay, no, I didn't say fact. Yeah. There was a raised hand. Bijay and Rai, you have a raised hand.
Sir, can we count the number of distinct vector spaces of distinct subspaces of vector space can have?
Can you count the number of
distinct subspaces of vector space can have?
Right. What do you think? We will come. Yeah, this is a good question. Yeah. So just ask me, say 10 minutes later.
Okay, sir.
Yeah, this is a good question. Yeah.
And sir, I also just have a quick question.
Right.
If you have two subspaces that have a non-empty intersection.
Wait. We have yet not finished with proposition. I have not proved the proposition. Okay. So before I prove the proposition, I should make sure that you understand the proposition. I put up a mathematical statement which has to be proved. So what does the statement say? Supposing I am given a vector space and I am given a non-empty subset which is closed under addition of vectors and scalar multiplication. First of all, does there exist a structure of vector space on that subset? What does that mean? I have to give the rest of the package. I have to give a zero vector, I have to define minus of a vector, and I have to make sure that various things are satisfied. And then I have to check that the inclusion map, which is only a map of sets, is actually a linear map. Right? So the first step is, okay, I have given this subset which is non-empty and is closed under scalar and vector addition and scalar multiplication. I have to give this a structure of a vector space. Okay. Now, what are the things that I need for a vector space? I need a zero vector. Okay, now I look around. Okay, look around for a zero vector, which some vector in the subspace that deserves to be called a zero vector. Now, an obvious thing would to do, and thanks for whoever suggested that I take this tack, is take the zero vector in V and ask, does this belong to this subset W? Because you remember in the characterization of W, that was nowhere mentioned. We said we know it's non-empty, and we know it's closed under addition of vectors and is closed under scalar multiplication. But it's nowhere mentioned that the zero vector of V belongs to W.
Yes, sir. If we multiply by scalar 0 with any of the vectors.
Exactly. So so the zero vector of V belongs to W, because we know, first of all, that W is non-empty. And this is the point that I had missed earlier, and somebody pointed out in a mail to me. Thanks for that. If it is non-empty, then I can take any vector that belongs to W and multiply it by the scalar 0. And since W is closed under scalar multiplication, that belongs to W. On the other hand, I know that the vector that I get is the zero vector of V. Therefore, the zero vector of V belongs to W. So at least there is a candidate for the zero vector in W. Similarly, given any vector in W, I must find its additive inverse, the minus of that vector. Now, that is okay, because I know that the minus of a vector in V is given by multiplying by -1. So I can, and because, so again, if I take a vector in W, think of it as a vector in V, the minus of that vector also belongs to W. So that's also satisfied. So the two major ingredients that make the four major ingredients that make a vector space are in place, because you already know it's non-empty. Addition of vectors we had assumed at the beginning, scalar multiplication we had assumed at the beginning, and now we have also got that zero vector and minus of a vector. Now it's a matter of checking that the rest of the package is satisfied. You take your red definition or your blue definition, or red definition as the minimum number of things to check. That is why that is useful. You check all the properties of the red definition and you're home. And then linearity of the inclusion map is essentially is built into what you already did. And because of that, uniqueness of the structure also will follow. So I'm not going to work through this. I might put this in the notes. I think I will do that. Okay. Now, having done this, now let us come back to examples and ask, and this is a good point to address the question asked by, I think it was Vijay and Roy. Can we count subspaces of a vector space? So the first example is take your vector space V to be R, the real numbers itself. Okay. Can you give me an example of a subspace?
0.
Very good.
Integers?
Sorry. Okay.
Sir,
First,
R.
Okay. So now we have three answers: 0, R itself. So Rishikesh Srinivasan says 0 and R itself.
So what is
Sir,
the
is R-
base field? So what are the, like, where are the scalars in? What is the field that you are assuming?
Where have you been? I said at the very beginning for the
No,
next
no, like
we are going to say real numbers.
No, sir. I mean, what are you like? If you want
for
an
this
example,
specific question, for this specific question, because other
No, I know. For this, we are still working with real numbers. Always real.
Okay, then just 0 and the entire space.
But actually, for this question, you can replace this by any field, and the answer will not change.
Sir, if natural numbers is a vector space including
Wait.
0.
Okay, let's see. There are too many people speaking. So there are. Let me give the possible answers. The one answer was if you just take the single element set 0, that is a subspace. Then the other, so this is a subspace of R. Then R itself is a subspace. And then a number of other things were suggested. Q, And somebody even said Z. Right?
So
Somebody
Z,
said, wait.
Z by empty is
See, I'm just putting down various answers. Then we will talk about it. So Soham Chatterjee said Q, and yeah, there are many. Somebody said Q. Somebody said I guess Q, integers, etc., etc. All even integers has been suggested. Somebody said the congruence modulo class, etc. Z mod NZ. Okay. Now, so okay. First, so before we come to the more exotic things, so let me just put down everything. And so somebody said Z mod NZ even, and somebody said even integers. So let me just quickly say, because just in case somebody gets bored and leaves, that in fact only these two are subspaces. Huh? So this is the only. So let me just. This is sufficiently important. This is correct. This is correct. The others are not subspaces. So let's deal with them. Okay. If I take even integers, that's certainly a non-empty subset of the real numbers, and it's even closed under addition. Yeah, it is. But is it closed under scalar multiplication? Yeah, Shakti Shayan says it's not closed under scalar multiplication, because if I take the even integer 2 and multiply it by the scalar 1/2, because half is certainly a real number, I get the integer 1, which is not an even integer. Okay, so the set of even integers is not closed under scalar multiplication. Now, this is true of all integers also. If I take the integer 1 and multiply by half, I get 1/2, which is not an integer. Even the rationals are not a real subspace, because if I take the rational number 1 and multiply it by the non-rational number √2, I go outside the rational. So the rationals are not closed under scalar multiplication if the field in question is always real numbers. Now Z mod NZ, I don't even know how it's contained in the real numbers. So we will not even go there.
Okay. Sir, earlier you said that even if you replace it with any field, that only zero.
Please, I don't. Let's just understand the real numbers, for heaven's sake.
Okay, sorry, sir. Sorry.
Yeah, let's just stick with real numbers until further notice. Okay.
Yeah. So
yeah,
can't we just say that any non-trivial, as in that's just not zero, any non-trivial subspace is immediately
no. So
just
the point is, when I said these two are the only subspaces, that's what goes into what your argument is. What goes into that? I said that only subspaces are 0 and R.
Yes, sir, I was just giving like a one-line proof.
Okay, yeah, sure, yeah. So I will leave this as an exercise, and the exercise will use your argument. Yeah, thank you,
sir.
Yeah.
Will it be like selecting all?
Vijayan, please keep. Okay. Just wait. Okay. So this was Rajdeep Ghosh, right?
Yes, sir.
Yeah, so I claim that the only subspaces of the vector space R are the zero subspace and the
full subspace
space R itself. Okay.
Yeah.
So here is the proof. If it's not the zero subspace, it contains one vector which is non-zero. In other words, some non-zero real number. Now, any other real number is given by taking this non-zero real number and multiplying it by a scalar. So if I have a subspace, that's contained, which is not a zero subspace, it's all of R. That's a proof.
Yes.
Okay. Very good. Now, what if I take V equal to R2? So let's think of a picture. R2, there are two ways of writing it. I can think of this as write it like x1, x2, xi reals, or as I prefer, I think of it as what I call a column vector. Xi real. And those who like pictures, R2 is just the xy. I will call this the x1 instead of xy plane. I'll call it the x1, x2 plane. So R2 is just a point in this plane. Consists of points in the plane. Okay. Okay. Now, what are possible subspaces?
So the two straight lines x1 and x2.
Okay. So the people have suggested two subspaces. So let me draw them. There is one subspace is this, and here is another subspace is this. Okay. Any other sections?
Like 0 itself and the entire plane and
Yeah, wait. So now there is a third subspace being suggested. Let me call it.
So
just wait. Just wait.
Yes. Sir.
The subspace consisting of 0. Okay.
The entire space.
R2 itself. Okay. R2
and
itself.
any line through origin.
Ah. Okay. Who said that?
Rohan.
Okay. So now there is a new construction. There is a new thing. Take any line through the origin. So now, of course, the red line and the blue line are examples of lines to the origin. So in the interest of removing ambiguity, being sort of just keeping things, having the minimal number of things. So let me just do it again. So, and all of R2. Okay. So, just one second. I've drawn the axis. Let me remove this point. So this is in the R2 plane, in the x1, x2 plane, there are, we have drawn 3 examples of subspaces, all of R2, first of all, not to forget that. Then the smallest subspace, which is 0, the guy here, and any line through the origin. Okay, so now we all agree that all of R2 is a vector space, and we all also agree that if I just take the 0 vector, that's a subspace. If I take the set, the singleton set with only the 0 vector, that is a subspace because it's closed under addition, and it is non-empty. It's closed under addition and scalar multiplication. But there is now a new character in town, namely the purple line, any line through the origin. Because if I take any point in this line through the origin, any 2 points, their sum belongs to the same line, and any scalar multiple of such a point belongs to that line. So clearly, any line through the origin is a subspace, and it is again exactly the same argument that I think Jasdeep Ghosh gave will prove that in fact these are all the examples of subspaces of R2, and this also proves that in fact there is a uncountable infinity of subspaces of R2. There are the big guy R2, there's a small guy 0, and there are all these one-dimensional subspaces, these lines to the origin.
Sir,
Yeah, so having said this, I'm going to come to a stop. I'm going to stop recording because the class is over. But give me 2 minutes to get my voice back and then we'll talk again.